Chapter 3, Lesson 1, the structure of matter. What is matter and what isn't matter? Is a glass with some water in it half empty or half full? Actually, neither is correct. The glass is completely full, half full of water and half full of air. But what is air? Air is a mixture of several gases, including nitrogen and oxygen, which are kinds of matter. Matter is anything that has mass and takes up space, so even though you can't see it or hold it in your hands, air is matter. What about all things you can see, taste, smell, and touch? Most are made up of matter too. Look at things pictured in Figure 1 and determine which of them are matter. Matter is something, if it has mass, matter is something that takes up space. If you look at the bottom of the page, you've got a rainbow. That's light. That's not necessarily going to have mass and take up space. You've got a sculpture and you've got a pumpkin. Both of those are matter because they have mass and take up space. What isn't matter? You can see the words on this page because of the light from the sun or from fixture in the room. Does light have mass or take up space? What about the warmth from the sun or the heat from the heater in your classroom? Light and heat do not take up space and they have no mass. Therefore, they are not forms of matter. Emotions, thoughts, and ideas are not matter either. Does this information change your mind about the items in Figure 1? Hopefully that reiterates what we identified as what was matter and what isn't matter. Well, what makes up matter? Page 73. Suppose you cut a chunk of wood into smaller pieces. Do the pieces seem to be made of the same matter as the larger chunk you started with? If you could cut a small enough piece, would it still have the same properties as the first chunk? Would you reach a point where the last cut resulted in a piece that's no longer resemble the first chunk? Is there a limit to how small a piece can be? For centuries, people have asked questions like these and wondered what matter is made of. An early idea. Democritus, who lived from about 460 BC to 370 BC, was a Greek philosopher who thought the universe was made of empty space and tiny bits of stuff. He believed that these bits of stuff were so small they could no longer be divided into smaller pieces. He called these tiny pieces atoms. The term atom comes from the Greek atom, which is defined as something that cannot be divided. Today, an atom is defined as a small particle that makes up most types of matter. Figure 2 shows the difference between Democritus' ideas and those of early scientists and philosophers. Democritus thought that different types of atoms existed for every type of matter and that atoms explain the characteristics of each type of matter. Democritus' ideas about atoms were a first step towards understanding matter. However, his ideas were not accepted for over 2,000 years. It wasn't until the early 1800s that scientists built upon the concept of atoms to form the current atomic theory of matter. Matter is anything that has mass and takes up space. The atom is a small particle that makes up most types of matter. Lavoisier, as we read in the next section, is going to introduce to us the law of conservation of matter. That matter is neither created or destroyed, but only changes forms. Lavoisier's contribution, page 74. Lavoisier, a French chemist who lived about 2,000 years after Democritus, also was curious about matter, especially when it changed form. Before Lavoisier, people thought matter could appear and disappear because of the change they saw as matter burned or rusted. They might have thought that matter can disappear if you've watched wood burn in a fireplace or at a bonfire. Lavoisier showed that wood and oxygen it combines with during burning have the same mass as the ash, water, carbon dioxide, and other gases that are produced, as shown in Figure 3. In a similar way, an iron bar, oxygen, and water have the same mass as the rust that forms when they interact. From Lavoisier's work came the law of conservation of matter, which states that matter is not created or destroyed, it only changes form. Before Lavoisier, people used to think matter could appear and disappear, and he proved the law of conservation of matter, that things aren't new or created or disappear. They've just changed form from one form of matter into another. The amount of that matter is actually still the same, just might be in a different form. Models of the atom on page 74. Models are often used for things that are too small or too large to be observed, or that are too difficult to be understood easily. One way to make a model is to make a smaller version of something large. If you wanted to design a new sailboat, would you build a full-size boat and hope it would float? It would be more efficient, less expensive, and safer to build and test a smaller version first. Then if it didn't float, you could change your design and build another model. You could keep trying until the model worked. In the case of atoms, scientists use large models to explain something that is too small to be looked at. These models of the atom were used to explain data or facts that were gathered experimentally. As a result, these models are also theories. Dalton's atomic theory. In the early 1800s, an English schoolteacher and chemist named John Dalton studied the experiments of Lavoisier and others. Dalton thought he could design an atomic model to explain the result of those experiments. Dalton's atomic model was the set of ideas, not a physical object. Dalton believed that matter was made of atoms that were too small to be seen by the human eye. He also thought that each type of matter was made of only one kind of atom. For example, gold atoms make up gold nugget, and a gold ring is shiny appearance. Likewise, iron atoms make up an iron bar and give it its unique properties, and so on. Because predictions using Dalton's model were supported by data, the model became known as the atomic theory of matter. Atoms are too small to be seen by the human eye, and each type of matter is its own type, made up of its own type of atoms. The size of atoms. Atoms are so small it would take about 1 million of them lined up in a row to equal the thickness of a human hair. For another example of how small atoms are, look at figure 4. Imagine you were holding an orange in your hand. If you wanted to be able to see the individual atoms on the orange surface, the size of the orange would have to be increased to the size of the Earth. Then imagine the Earth-sized orange covered with billions and billions of marbles. Each marble will represent one of the atoms of the skin of the orange. No matter what kind of model you use to picture, the result is the same. An atom is an extremely small particle of matter. Discovering the electron. Here we have a cathode ray tube that's going to be described. It's going to send an electrical current through this tube, and that is going to allow us to see the behavior of some electricity and how we have discovered the negative part of an atom, the electron. One of the major pioneers, or many pioneers, in the development of today's atomic model was J.J. Thomson, an English scientist. He conducted experiments using a cathode ray tube, which is a glass tube sealed at both ends, of which most of the air has been pumped. Thomson's tube had a metal plate at each end. The plates were connected at high voltage electrical sources that gave one of the plates, the anode, a positive charge, and the other plate, the cathode, a negative charge. During his experiment, Thomson observed rays that traveled from the cathode to the anode. These cathode rays were bent by a magnet as seen in figure 5, showing that they were made up of particles that had mass and charge. Thomson knew that like charges repel each other and opposite charges attract each other. When he saw that the rays traveled toward a positively charged plate, he concluded that the cathode rays were made up of negatively charged particles. These invisible negatively charged particles are called electrons. Why were the cathode rays in Thomson's cathode ray tube bent by a magnet? Because that magnet has a positive and a negative charge, and if those charges are opposite of each other, they would be attracted to each other. If they are the same, like charges are going to repel. Try to imagine Thomson's excitement at this discovery. He had shown his atoms are not tiny to divide after all. Rather, they are made up of even smaller subatomic particles. Other scientists soon built upon Thomson's result and found that the electron had a small mass. In fact, an electron is 1,837th of the mass of the lightest atom, the hydrogen atom. In 1906, Thomson received the Nobel Prize in Physics for his work on the discovery of the electron. Matter that has an equal amount of positive and negative charge is said to be neutral. It has no net charge. Because most matter is neutral, Thomson pictured the atom as a ball of positively charged with electrons embedded in it. It was later determined that the neutral atoms contain an equal number of positive and negative charges. Thomson's model. Thomson's model, shown in figure 6, can be compared to chocolate chips spread through a ball of cookie dough. However, the model did not provide all the answers to the questions the puzzle scientists thought about atoms. So Thomson discovered the electron, and then he created his own model that believed that those negatively charged particles were in the middle of what would be kind of like a cookie dough model, and those negatively charged particles, the electrons, they would be the chocolate chips themselves in that chocolate chip cookie dough. Number 6 is on page 77, Rutherford and the nucleus. Scientists still had questions about how atom was arranged and how the presence of positively charged particles. In about 1910, a team of scientists led by Ernest Rutherford worked on these questions in their experiment. They bombarded an extremely thin piece of gold foil with alpha particles. Alpha particles are tiny, high-energy, positively charged particles that he predicted would pass through the foil. Most of the particles passed straight through the foil as if it were not there at all. However, other particles changed direction, and some even bounced back. Rutherford thought the result was so remarkable that he later said it was almost as incredible as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you. Positive center. Rutherford concluded that because so many of the alpha particles pass straight through the gold foil, the atom must be made of mostly empty space. However, because some of the positively charged alpha particles bounce off something, the gold atoms must contain some positively charged object concentrated in the midst of the empty space. Rutherford called the positively charged central part of the atom the nucleus. He named the positively charged particles in the nucleus protons. He also suggested that electrons were scattered in most of the empty space around the nucleus, as shown in Figure 7. On page 78, discovering the neutron. Rutherford had been puzzled by one observation from his experiments with nuclei. After the collisions, the nuclei seemed to be heavier. Where did the extra mass come from? James Chadwick, a student of Rutherford's, answered this question. Alpha particles themselves were not heavier. The atoms that had been bombarded had given off new particles. Chadwick experimented with these new particles and found that, unlike electrons, the paths of these particles were not affected by the electric field. To explain this observation, he said that these particles came from the nucleus and had no charge. Chadwick called these uncharged particles neutrons. His proton-neutron model of the atomic nucleus is still accepted today. Improving the atomic model. Early in the 20th century, a scientist named Niels Bohr found evidence that electrons in atoms are arranged according to energy levels. The lowest energy level is closest to the nucleus and can hold only 2 electrons. High energy levels are further from the nucleus and contain more electrons. To explain these energy levels, sometimes it's thought that the electrons might orbit in an atom's nucleus and pass at specific distances from the nucleus, as shown in Figure 8. This is similar to how the planets orbit the sun. The modern atomic model. As a result of continuing research, scientists now realize that because electrons have characteristics that are similar to waves and particles, their energy levels are not defined planet-like orbits around the nucleus. Rather, it seems more likely that electrons move in what is called an electron cloud. The electron cloud is a spherical cloud of varying densities surrounding the nucleus. The varying density shows where an electron is more or less likely to be. Atoms with electrons in higher energy levels have electron clouds or different shapes that also show where those electrons are likely to be. Generally, the electron cloud has a radius 10,000 times that of the nucleus. Further research. By the 1930s, it was recognized that matter was made up of atoms, which were in turn made up of protons, neutrons, and electrons. The scientists called physicists continued to study basic parts of this atom. Today, they have succeeded in breaking down protons and neutrons into even smaller particles called quarks. These particles can combine to make other kinds of tiny particles too. 6 types of quarks are up, down, strange, charmed, top, and bottom. Quarks have fractional electrical charges of plus 2/3 or negative 1/3, unlike that plus 1 charge of a proton or negative 1 charge of an electron. Research will continue as new discoveries are made about the structure of matter.